Good afternoon, everyone, and welcome to the Simons Lections, 2019 Simons Lections. So my name is Michel Gomens, and I'd like to welcome you to the mathematics department. So we have had these Simons Lections for the last 20 years after a gift of Jim Simons. As you know, Jim Simons' philanthropy is infinite, and we are in the Simons building. There are a few Simons professors in the audience. There are some Simons fellows, some Simons investigators, and so on. So typically we have two sets of Simons lections. So the first set is given by Sasha Barvinok, and that's going to be today, tomorrow, and Friday. And then we have a second set next week by June Hu on Monday, Tuesday, and Wednesday. Same room, reception also half an hour before upstairs. So both sets of lectures on geometry of polynomials to some extent, but they will be quite different, I presume. And so let me introduce Sasha. So Sasha is a professor at the University of Michigan, and his research is connected to algorithms and understanding the complexity of problems at the intersection of geometry, algebra, and combinatorics. Let me give you one very classical result of his from 25 years ago, which is easy to state and quite remarkable. So you take a polytope in dimension D, so a finite intersection of half spaces, and what you'd like to do is you'd like to count the number of integer points in the polytope. So in 2 dimensions, so it's quite simple. So there is Pick's theorem or Pick's formula that gives you a relationship between the area and the number of points on the boundary, and you can deduce the number of lattice points or integer points inside the polytope. So that's in 2 dimensions. There was a way to compute it in 3 dimensions and 4 dimensions. What Sasha did a quarter century ago, that doesn't make us...
last millennium, yeah.
Last millennium, yes, last millennium. That's another way of saying it. He developed an algorithm which, for fixed dimension, gives you, in polynomial time, allows you to count the number of such lattice points. So that's just a small glimpse of his research. Sasha has received a number of prizes and so on, including a Pegazi award from then President Clinton. At least at that time, the country had still some moral compass to reward science. But in any case, you didn't come to listen to me, so let's give a big applause to Sasha.
Thank you very much. So yeah, I'd like to compute things, and these 3 lectures will be about computing some particular creatures that I would call informally like big polynomials. And what are big polynomials? So it's not a formal definition, but basically the idea is that you have a multivariate polynomial, and we will always consider either real or complex, more often complex than real. And what we know, so we know that the polynomial is indeed too big. It takes too long to write all monomials there. But on the other hand, we know what we're dealing with, because for every monomial we can quickly compute its coefficient, if not zero, or zero, in the polynomial. So we can quickly its coefficient. So, and of course, we'd like to have an example, right? So one example is pretty standard. It's the determinant. So if we have a square matrix, right? So we all know what the determinant is. It's the sum over the whole symmetric group, the sign of the permutation times the product of the generalized diagonal. And it sort of perfectly fits the description, right? So like for n equal 10, it's already too long, right, to write all the monomials there. But we know what are they, right? So for every particular monomial, we have no trouble saying if it's in there, and if it's in there, and with what coefficient, plus or minus 1, right? So it's a sort of typical example. So what I'd like to do, I'd like to be able to compute these polynomials. So we want compute the value. We want to compute preferably exactly, or failing that, approximately. The value. Right, of a polynomial. So, and it's not a fanciful question, right? So we would like to be able to compute determinants, for example, right? So that's sort of the rough description of the objects we'll be dealing with. So any objections to that? That's exactly right. That's what we're going to talk about most of the time, right? So, right. So when we look at the determinant, so we know that some classical algorithms, so for example, Gaussian elimination does it roughly in n cube arithmetic operations, which is considered to be pretty good. So we can do it faster if we use various tricks. We can do it a little slower, but still quite fast if, for example, we want to compute the determinant over a commutative unital ring. So we disallow divisions. It's still possible, right? So, and what we want to do here, so we want to compute exactly approximately, again, sort of roughly in polynomial time, in using this many operations, right? So, okay. Now then, so the observation that people made and it's sort of said that practically the determinant is the only thing we can compute, really. I'll put it with a little qualification, is pretty much. The only thing we can compute. I put pretty much because there are various sort of cousins and ramifications. So example, well, here there are plotins, for example. which we can compute, but they're basically determinants, right? So it's basically a square root of the determinant. So, and you can play a little bit with it, and still you don't get things very much different from the determinants. So it's an observation. It's not a theorem. It's a bit of a mystery. So, yes. Yeah. Yeah. Thank you for sort of. I didn't plant these people here. They'll ask all the right questions. They are determinants too. Yeah. So yeah. In fact, everything, right, that's a straight line program can be written as a determinant. And that doesn't quite explain things, right? Because there are other things that are other than straight line programs, and still the determinant seems to be very basic. So that would have been the end of my talk, right? But we want to do something, right? So if we cannot compute it exactly, we may want to compute it approximately. So what else may we want to compute? So example that I'll put probably here, or maybe there. So is the permanent. That's what Alex suggested, so permanent. So the permanent is defined by, it looks even simpler than determinant, so there are no pesky signs. It's the sum over all permutations just of the generalized diagonals. And historically, it's my understanding that they were introduced together with the determinant in or about 1812 by Cauchy and also Binet. So it was a fateful year in many respects, right? So the Napoleon Wars raged in Europe. Well, this kind of a proxy war here, right? And Cauchy and Binet introduced the permanent. So just to nail it, right? So, then what happened? So why do we care about the permanent? So in 1970s, 1980s, Valiant sort of explained that if we can compute the permanent, we can compute almost everything. So again, exactly. So it's sort of a universal problem. So I will not probably put a qualification here on almost everything, so because it was done in several settings. So in sort of called sharp p-hard setting and also in algebraic setting. One disclaimer though, so it doesn't help us to compute almost everything, but it makes us feel better about not being able to compute the permanent, right? Because if we could, then we could do too much, right? So in fact, I'd like to state one of his questions. So it's a version of P versus NP question, sort of algebraic incarnation. So what it says that other affine maps from the space of complex matrices n by n to the space of complex matrices of larger size, such that so the first thing is that the size gets blown up at most polynomially. So, and second, magically, the permanent gets transformed into the determinant. So the permanent of A is the determinant of T of A. Right. We don't know. So, and I'd like to state it here because if you never thought about P equivalent P and all this stuff, and if you sort of read the, yes? To its affine. Affine means it's a linear plus constant, right? Yeah. So a map. So made it corresponding to its permanent. It's a map. I agree with that, right? But it's not an affine. I like to have an affine map. Right? So, and if you never thought about P equivalent P, then to get into the business looks a bit clunky because you have to read about Turing machines and other stuff, right? And not everybody enjoys this. But this is a perfectly, I said not everybody, I didn't say no one, right? So no, I personally do, right? So, and the majority, I'm sure, also do enjoy that, right? So, so here's a question that's sort of parallel algebraic shape. And if you never thought about it, I'm just hoping that maybe you just get some fresh ideas, right? And just prove it, right? So the common belief is that it doesn't really. It cannot be done. So the best we know is that the dimension has to be blown up at least quadratically. And part of the problem is that if we allow the dimension, well, it's tempting to say, well, we can never find an affine map like that, but that's not true. So it's easy to construct a map where n just up to a polynomial factor is 2 to the n, right? Capital N is up to a polynomial factor 2 to the n, right? So, right. So that's the P equivalent P question, one of the incarnation. I think the incarnation that everybody can sort of appreciate, right? And it's also sort of underlines the importance of the permanent question, right?
Sorry, can you say what the omega means?
Yeah, so that means that there has to be, yeah. So that means that for some positive constant, you have this, right? Maybe I should say you have this for some positive gamma, right? So, okay. Right. So the situation, therefore, with exact computation is pretty dire. We cannot do anything, well, other than determinant. We cannot prove anything either, right? So that we don't like. And therefore, we ask about approximate computation. And with approximate computation, the situation is much more nuanced. So, and it's impossible to cover, like in 3 lectures, what we know, what we don't know. So what I'd like to talk about is just one particular side of it. It's the relation between the complexity of approximate computation. And complex zeros. On the polynomial. Right. So, and that will be the main topic for these 3 lectures, right? So again, so it's probably a good time to pause because I'll start erasing things and ask if there are any objections. Complex could be real. Yeah. Could be complex, could be real. Right. Yeah. More or less. More or less, it means that they're not equal. Yeah. Yeah. It pretty much nails it without mentioning ever Turing machines.
So if you get any here it's VP. Here it's VP versus VP.
Yeah, but we all agree that will be quite a big thing, right? Yeah.
So you get $1 million if you answer.
I cannot personally vouch for that, but I'll do my best that you get it. Okay. Yes? Well, yeah, but coefficients are easier to. Everybody knows what coefficient is, right? And with circuits, opinions differ. So, yeah. Okay. Oh, yeah. I'm sorry, what? There are problems that are probably hard to approximate. Yeah. Yeah. Oh, yeah. No, that's big O. Yeah. Yeah. No, it doesn't. But affine is simpler. Everybody knows that an affine map is. Okay. Yeah. Okay. So I'd like to give a taste of what is to follow. What will follow? I'll state. I think I erased this part and that part. And I'll state 2 theorems as an illustration of what I mean by connecting zeros to the computational complexity. So here's what I will call theorem 1. Theorem 1 says that let Aij be n by n complex matrix such that all entries are within distance 0.5 from 1. So then the permanent of this matrix is non-zero. So that's one theorem. From theorem 1, we will deduce theorem 2. So there are complex. Yeah, I assume the knowledge of complex numbers here. Yeah. So right. Complex, right. So, Alex, we're still friends, right? So, okay. Yeah, from that, I'd like to deduce what I call theorem 2. Maybe I'll put it here because I'd like to have them the same time board. Theorem 2, which will appear as an immediate corollary of Theorem 1. So for any epsilon greater than 0, well, let's make it less than 1, for any n integer, right? There is a polynomial p, which will depend, of course, on n, on epsilon. It will be polynomial in the matrix entries, in the entries of an n by n complex matrix. Aij, such that the polynomial has a very low degree. The degree of the polynomial is basically logarithmic in n. And the constant here in the O notation is absolute. So I don't know, 2. And second, we have the log of the permanent of A approximated by this polynomial with an error epsilon, provided a slightly tighter condition is met. All entries are within distance 0.49, say, from 1. Right, so basically what happens here is that once we established that the permanent doesn't turn into 0 in some domain, we can approximate it efficiently, what's called in quasi-polynomial time. So this polynomial is computable, what's called quasi-polynomial n to the O log n minus log epsilon time in a slightly smaller domain, right? Yeah, right. Thank you. Yeah. Log n, right. Yeah. So, and Theorem 1 will, so we'll develop a certain machinery. It's not very complicated, though, which will sort of give us Theorem 2 immediately from Theorem 1. So now I'd like to make a couple of comments. So one comment is, if you get bored or already bored, I suggest you spend the rest of the time here on proving this theorem. It's not very hard. So second, yeah, I'll show you a proof tomorrow. But by tomorrow, I can also post challenges. So one challenge is I have no idea if the constant 0.5 is optimal. So find, or improve, rather, improve 0.5 or show it's optimal. The trouble is that for 2 by 2, you can do it without computer. For 3 by 3, you cannot do it with computer. It's just some system of polynomial equations of degree 3 in 9 complex variables. Pretty symmetric. It's not so easy. Well, I couldn't. Well, I couldn't because I cannot compute anything. But people tried, and they didn't. So, yeah, sure.
Theorem 2 has a logarithm of the permanent. Is there automatically in Theorem 1 some restriction on where these non-zero values live?
No, because what happens, right? So you have non-zero on a simply connected domain, so you can take a branch.
Sorry, what's the simply connected?
The polydisk. The polydisk of all matrix entries, right?
But you're taking the log of the permanent.
That's true. So I have a function, right, which is non-zero, right, on a simply connected domain, so I can take a log, right?
The point is in the center of this disk, this permanent is n factorial, so log n factorial is a well-defined thing, and then you take that branch, right?
For example, yes. So improve 0.5 for sure it's optimal. And second, it's sort of more of a philosophical nature. For the optimal constant, because there is an optimal constant, do we get a non-strict inequality or strict inequality in the optimal formulation? I don't know the answer, and I don't know what kind of mathematics can you possibly use here to answer that. If you prove the optimal version of Theorem 1, so does it come with strict inequality and non-strict? Because in any particular dimension, of course, it should come with strict inequality, right? So it's a closed variety, and you measure L infinity distance to that variety, right? But as the dimension grows, things can go wild. So the question, do they or don't they? Yeah, and I don't even know what kind of math can you possibly employ here or there. The proof, actually, that I'll show you tomorrow, all you figure out today, is uses middle school math, not more. Yeah. I'd like to make a couple of remarks. Yes? No. Just no, generic. Not brand name middle schools, just generic, sort of ideal. So remarks. So the theorem is not exactly obvious, so this non-zeroness, because, so what do you say? You say that the entries are in the disk centered at 1 of radius 1/2. And for example, if they're all the same, then a permanence is just n factorial times a to the n. So as your entry walks around this disk, the permanence walks all around the complex plane, right? So it's not confined to any particular sector, but it never hits 0, right? Somehow, yeah. So that's the first remark. So the second remark is that you cannot. So the second remark is that the permanent of one particular matrix is 0, which is the matrix of 1 plus I over 2, 1 minus I over 2, 1 minus I over 2, 1 plus I over 2 is 0, from which it follows that you cannot replace 0.5 with square root of 2 over 2, which is approximately 0.71. So furthermore, if you think that, yeah, by the way, square root of 2 over 2 is optimal in dimension 2. I think that's what we know for sure. This is it and nothing more. Everything else is kind of shaky. So furthermore, what happens that you can construct a matrix of an arbitrarily large size with this distance to the matrix of all 1. So if you just multiply it by Kronecker by a matrix of an odd size, that's observation of Boris Buch, then you still get 0, right? So, on the other hand, people tried 3 by 3, and for n equals 3 by 3, I was told that some experimenting say that you cannot replace 0.5 with 0.677. Right, but even for 3 by 3, it's already not known. Maybe serious people who really can compute. Maybe they didn't try it, but everybody I asked, so they tried it, and they say that they cannot do it numerically, but they can sort of strive for a record. And that's the current record at n equal 3, right? So, so the last remark here is, so this actually works. So for so remark, for 20 by 20 matrices, that's where Maple can still kind of spit out an answer in reasonable time. So polynomials of degree 3 appear to produce about 1% error, although for log of the permanent. So that's done by then integrated, so Max Kantorovich and Hanbu. So I put it here to say that, I mean, this theorem is correct, is true not only in general, but in particular, meaning that you can just use it to compute things. Okay. So, yes? Well, they just tried and tried and tried, and it seemed to work. Well, whatever they could come up with this condition. Well, first they tried random, then they tried what they think would a bad matrix would look like, and yeah. So no, it's not a theorem; it's a remark. Right? So yeah. But we don't have any intuition really. What's the worst case scenario here? Yes.
So do you know anything about hardness if you replace the constant? I mean, so are there, if I replace the constant with something much smaller than 0.5?
No, much smaller is okay. Much larger, right?
Sorry,
So with 1, then it's getting harder, right?
Yeah.
With other than that, I don't really know. No, I don't know. No.
Is there a reason why you use L infinity norm rather than some other norm?
Which one? Do you have an idea? L2 is pretty bad because you can make a row of zeros, and you're done in 4, right? So L2 is very sensitive. What you can do, you can take the sort of the hybrid of L infinity L1, taking the max of L1 norms along rows and columns, then you get a similar asymptotics. But I gave it as an example because it's really easy to prove, as you'll convince yourself either tonight or I'll convince you tomorrow. Yes.
By your remark, because using the theorem, you said the constants were explicit. Can't you apply the theorem and get the polynomial and know that exactly what?
Well, it's what you get is a sequence of polynomials as a family, and you say that you can pick from that family a polynomial of a sufficiently small degree that does approximation, but that doesn't preclude you from picking a polynomial with a much smaller degree from the same family. So it's for which nothing is guaranteed, and to see how it works. We'll see it from the proof. Okay. So other objections?
If you know this 20 by 20 thing, does that actually make these other computations of valiant consequences?
No, it's of no consequence. It's just nice to know that numbers do not lie, right? So I prove a theorem, but who knows, right? And then you get in a number, and the number is correct, so I must have done something right. Makes me feel better. Well, for a complex, for real positive or non-negative, right? But it's just an example, right? So I'm just saying it's an example. Okay, so I'd like to, right, so that's about time to state where this, is it time? Not yet. So I'd like to say just a few words. So why do we care about permanence? So of course, sort of valiant sort of theory that it's a universal question, that's helpful. But it's just a really quick remark, so that permanents have a sort of meaning of their own. So why permanence? So the first sort of application, if you wish, or in combinatorics, where they count things. So if you have what's called a bi-adjacency matrix of bipartite graphs, so it's 1 if you got an edge, and 0 if not. Then, so the picture is you have a graph, bipartite graphs, and some vertices on the opposing sides are connected. So, and then the permanent really counts something. So the permanent of A, in this case, is the number of what's called in combinatorics perfect matchings. Or what physicists would call dimer covers. Right. So, but then there are some integrals that arise in physics that are expressed as permanent. So I'll put physics in quote unquote. So it's because I don't know much about it. So suppose that you have a complex n-dimensional space with Gaussian measure one over pi then e to the squared norm of z, where squared norm is just the sum of the squared coordinates, right? So it's a probability density. And suppose you have a bunch of linear functions. Two families, so each has n functions. And what you want to compute the expectation of the product of the functions from one family times the product of the function of the other family, but complex conjugate. And then there is a famous formula. So it's actually the permanent of the matrix A, where Aij is the set of cross correlations. It's a Wick's formula, of course. So it comes in handy if you deal with bosons, right? It's actually very easy to prove, so I'll just prove it now. So you just notice that both parts are sort of linear in F and sort of quasi-linear in G, and therefore it suffices to check when F and G are all the same, and then it's trivial, right? So, okay, so permanents have sort of meaning of their own, right? Okay. So now then, so I'd like to start sort of building this bridge between Theorem 1 and Theorem 2. And that's what I call the interpolation lemma. So it's not per se a lemma. It's a sort of, as people say, a trivial but useful remark, right? So, so suppose we have the following situation. So let U be a neighborhood of a path connecting 0 and 1. So the picture is therefore is this. So the path is not important. The neighborhood is sort of more important. So somewhere here you have 0. Somewhere there you have 1. Then you have a neighborhood of this path. Let's call it U. So then there is a constant, a positive real number, depending on that neighborhood alone, so that the following holds. So if you have a polynomial, univariate polynomial, I'd like to have the degree or the number of terms listed, at least 2. It doesn't really matter. It just makes the theorem literally correct. So, such that the polynomial is not 0 in that neighborhood. Then for any epsilon between 0 and 1, the value of P of 1 up to a relative error epsilon is determined by the first very few coefficients. So is determined by the coefficient C sub k with k basically logarithmic in n. And furthermore, it can be computed from those coefficients efficiently in polynomial time. So, and can be computed in polynomial time. right? Oh. Oh, there. Right. So, so what happens here? So you fix a neighborhood. So you have some path from 0 to 1 in the complex plane. You fix a neighborhood. This neighborhood gives you a constant, which makes the interpolation sort of trivial. Basically, you say that if you want to compute the value of your polynomial at 1 with an error epsilon, then what you do, you just look at the first logarithmically many coefficients, and you ignore the rest, and that will do the job. Right. So I should probably say what do I mean by relative error, since we're dealing with complex numbers here. But that's the most sort of intuitive thing. So we say that, say, W1, which is not 0, approximates W2, which is not 0, within relative error epsilon if we can write W1 equal e to the z1, W2 equal e to the z2, with z1 minus z2 not exceeding epsilon. Right. So, okay, so that's what we'll prove. I'm not sure about today, but definitely tomorrow. Again, so it's not very hard. It's more like a trivial but useful remark. So before I show how this remark works in going from 1 to 2, so are there any objections? There's no, no. Right, yeah, right. Yeah. Yes. Yeah. Okay. So, so how does it work, for example, in this setting? So suppose I want to deduce 2 from 1. So deduce 2 from 1. So that becomes pretty easy, because what I do, I have to come up with my polynomial. So I say that, okay, so let A be a matrix such that that satisfies the conditions of theorem 2, actually, right? So the distance to 1 does not exceed 0.49. So I have to come up with a polynomial. So let P of z be the permanent. And I do just direct interpolation from the matrix of all ones to that particular one. So it's the matrix of all ones plus z times the matrix A minus the matrix of all ones, right? So that the value that I care about is the value of this polynomial at 1, right? So it's a polynomial of degree n, all right. And now theorem 1 says that what happens is that it's non-zero in a circle So P of Z is not 0 if Z does not exceed 0.5 over 0.49, which is greater than 1. So the picture is we got our neighborhood, right? So, well, it's a better picture, so better one here. So we have 0, we have 1, and we got a neighborhood. So 0, 1. So which we call neighborhood U. So it's a polynomial of degree n, right? So the value, so up to relative error epsilon. So the value at 1, so P of 1, which is a permanent of A, is determined by just logarithmically many coefficients, by basically the derivatives at 0, right, for k logarithmic in n and in epsilon. And then it we just compute those derivatives and see what they look like. So I'll continue here. Right, so what do we have here? So what's this derivative really is? So it's the case derivative at 0 of the following polynomials. So we take the sum over all symmetric group, right, of the product 1 plus Z AI sigma I minus 1, right? And substitute Z equals 0, right? That's what we do. And we know how to differentiate the sum. And furthermore, we even know how to differentiate the product, right? So it's the sum of all permutations. And what happens when we differentiate the product? So when we substitute Z equals 0, so we get a bunch of 1s. So what we collect is the sum, right, of overall ordered k tuples of different indices of what? A1 sigma of I1 minus 1 ik sigma of ik minus 1, right? But then it's a very symmetric situation, right? So when we sum overall permutations, so what we really get is n minus k factorial times the sum over collections of distinct indices of the products. Right, which, as we observe, is a polynomial of degree k in the coefficient. So polynomial of degree k in Aij. Right. And that pretty much does it, because the lemma tells us that we have to, if we want error epsilon, we don't go very far. We just collect these sums for k logarithmic in n in epsilon, and that gives us the approximation, right? So, okay, so I guess, yeah, I didn't prove anything. That's kind of pity. Well, I proved that the permanent of that matrix is 0. So 2 by 2, yeah. But I'll promise, I'll prove something eventually. Yeah, tomorrow. Yeah, it's probably a good time to stop.
Any questions?
For the what? For the well, so what it means is that if you just give me those coefficients that prescribed by that lemma, I will return you the number which approximates. Yes, it will be a function. It will be a polynomial, not necessarily Taylor polynomial. It's a function, right? Measurable.
Use the reference point, the matrix which consists of 1.
Yes.
But is it possible? So why do you choose? I mean, I understand that.
Because it makes my life, as you can imagine, much easier, right?
Right, but is it? Can one consider other reference points of this sort and prove a similar?
Yes, you can. Yes. Yeah, but that's perhaps the easiest example where we can see the moving parts. Sort of, yeah. Right.
This is interpreted as, you can interpret this as a partial sum of the partial partial metric,
Yes, of course, yes.
so that gives some new relationship between variance.
Yes, I'll talk about it tomorrow. Yeah. So basically, it's all here, and it's not very hard. No.